Hello everyone. We already discussed substitution reaction in aliphatic compounds, SN2 mechanism. Today we are going to discuss SN1 mechanism. So basically, SN1 is the full form is a substitution nucleophilic unimolecular. So if you look at the reaction mechanism, is that this is the any halogen compound you can consider, and I took that it is a chiral molecule because you can see all the four substituents are different here. The first step is to release the leaving group, okay, that produce a carbocation and a bromide ion, and they are always stay as a ion pair. Okay, then you have a nucleophile which can come from either side because your carbocation is sp2 type, and therefore both direction it is possible to attack the carbocation because carbocation is a planar molecule, so the nucleophile can either come from the top or the bottom, so you can have two different isomers. Okay, and if you consider the rate of the reaction is basically rate constant and multiplied by the concentration of the substrate, and this is because this is the rate determining step. Okay, now this is a two-step process, as you can see here. So first step is the release of the leaving group, and then you produce a carbocation intermediate, and then the nucleophile will come and attack to the carbocation, and that can lead to the two different products. Okay, so the activation barrier could be that the energy difference between that substrate and the first transition state, that is we call the the activation energy for this particular reaction. Let's talk about that which species, because we have now substrate as well as we have that nucleophile, which will be which will influence the rate of the reaction. And if you change the concentration of the substrate and measure the rate of the reaction, you will find it constantly increasing with increasing the concentration of the substrate. On the other hand, if you change the concentration of the nucleophile, the rate of the reaction will never change because it does not depend on the rate, or rate doesn't depend on the concentration of the nucleophile. And that actually clearly states that the rate of the reaction is depends on the concentration of the substrate, and we can write the rate equation for this particular substitution reaction unimolecular or SN1 reaction like this way. So what about the stereochemistry? So as I have mentioned earlier is that when you have a carbocation that produce after leaving that the leaving group, you produce a sp2 hybridized carbon. Okay, so you have a planar carbon, and the pi orbital will be, which is the empty orbital, will be like just which is perpendicular to the plane, and then the nucleophile with a pair of electron can come either from this side or from that side. So basically you can see the racemic mixture, so both R and S equal quantity if you have a single chiral center. But this is not always the true case. The reason is that when you have the leaving group which is just about to leave the molecule, you already produce sufficient amount of positive charge on the carbon so that the nucleophile start coming from the backside. Okay, and because of that particular reason, that you always have some enantiomeric axis which is like opposite chirality. Okay, so if you start with the R, you may end up with a little excess of the S. Now, having said that, it is only valid when your priority group is the same. For example, the bromine which is leaving the molecule, if that is that is the first priority group, and then the OH minus which is coming as a nucleophile, that should have this should be the first priority as well. If it is not, then R is that whatever I talk about, that R will change to S, or a little bit enantiomer matrix of S, that may not valid. So it may be R as well. But the if that means, then you always have certain excess of the in other enantiomer which is opposite chirality. Okay. Okay, so here you can see that I have given you that the way to predict this one. So you have bromine 1, R, for if you have any aliphatic chain which is 2, and then deuterium 3 and hydrogen 4. So hydrogen behind the plane, so you have anti-clockwise, so this is the S. Now when you check the first product, which actually coming from the back side, which is basically you have that Now you can check that priority rule. So this is 1, 2, and then 3. So it is sorry, 1, 2, 3. So I just made a mistake. So which will be the first? So and the R will be 2. So it will be like clockwise. It should be the R, and the other one should be the S because it is 1, 2, 3. So because you are getting R and S enantiomers. Okay, and I told you because of that ion pair effect, or that before the bromide leaving completely, the nucleophile start attack. Now here you can see something which I forgot to mention, that I make this reversible. Now this is very important to understand, because when the bromide leaves the molecule, it can come back because it's a positive cationic and the anionic species. They can again combine and come back to the static material. Okay, so this the first step is actually to some extent a reversible process. Okay, okay. So eventually we end up with the racemic mixture. And here I was talking about tight ion pair, because once they leave, the bromide ion does not leave completely, because they're always forming the tight ion pair. And if your molecule is this one and the bromine is this one, then bromine will be negatively charged, so OH minus will not able to come from this side. It has to come from the other side of the molecule. So that's why you have the inversion to some extent. Theoretically, we should have the racemic mixture, but because of the tight ion pair, or before the bromide leaves the molecule completely, the nucleophile start coming from the backside. So you will always have some sort of the inversion in chirality. So basically, if you start with S, you always have a little bit excess amount of R in your reaction mixture. Okay, what about the reactivity of carbon center? Because this is very important factor when you perform a reaction that follows SN1 reaction. Because you have to always understand the intermediate. Okay, if your intermediate is stable, then the whole activation energy will be coming down, and then or energy will be less, and then your reaction will be much faster. Okay, so the idea of SN1 reaction will be always to stabilize your intermediate carbocation. There are three different ways you can stabilize the carbocation. One is that hyperconjugation. So that we may discuss in a different topic of reaction intermediates. So here just I will give you a very simple idea that if you have MTP orbital, and if you have a CH bond, that is alpha to that position, and that sigma field or field sigma orbital, it should be parallel, because if they are not parallel, they cannot overlap. Okay, so when they are parallel to each other, so this electron can be donated. So we call no bond resonance or hyperconjugations. Okay, this is one of the way you can stabilize the carbocation. There's another two way. If you have a heteroatom like oxygen, nitrogen, sulfur, that have a pair of electron, that can be donated, that electron can be donated to the empty pair orbital. Again, you can see that I have arranged, or that I drawn it as a perpendicular to each other. So there should not be any angle between them. Okay, so they should be always perpendicular to have a proper pi overlap. Or the other case, you could have a unsaturated double bond or triple bond. So these orbital have a pi bond that can also stabilize your carbocation by resonance. So these are the three different ways you can stabilize your carbocation, and if you have these three effects, then you have a better chance to have the SN1 reaction. Okay, so always remember, whenever you think about that I want to perform a reaction which should follow SN1 reaction, then these three criteria should be present at the carbon. Either the carbocation should be stabilized by hyperconjugation, or you have a heteroatom which can stabilize by donating the lone pair, or if you have an unsaturated double bond, that can also stabilize your carbocation. Okay, so these are the few things that you probably have seen in your textbook, that this particular compound cannot undergo solvolysis reaction. So this is tertiary carbon. So you can see have two CH proton, two CH proton, two CH proton. So total 6 CH protons are there. So you can have possibly hyperconjugation. But the problem is that they are, for SN1 reaction, you need to produce a carbocation that is at the base head position, which is very strained, and that cannot be formed. At the same time, the orbital that would produce after leaving that OTS group, OTS is a sulfonyl, para-toluene sulfonyl group. So that OTS, that orbital which will be formed, that will be not parallel to either of the CH bond. So you cannot stabilize by the hyperconjugation. So this kind of compound never go SN1 reaction, neither SN2 reaction. So if you remember, we discussed earlier in our previous class. Okay, so that's what I was talking about. So BZ carbocation, which are really unstable because it requires it will be sp2 carbon, requires 120 degree, and that is not possible. Okay. So let's take an example of how this SN1 reaction could happen in presence of your heteroatom like oxygen. So we can say this is acetal or ketal. So this is the protected form of aldehyde or ketone. So if it is aldehyde, one of the R should be hydrogen, and if both are aliphatic, then aliphatic carbon chain, then we can say it's a ketone. So if it is ketone, we call it is a ketal. If it is a acetal aldehyde, we call this acetal. Okay. So what happened if you add acid? So you first protonate it. Okay, and that protonation, there are two different mechanisms possible. One case, it can directly release the alcohol, methanol in this case, and then you produce the carbocation, which can be stabilized by the lone pair present in the oxygen atom. And then in this particular intermediate, the water molecule can attack, then you produce another intermediate, and then it can come back and produce the ketone. Okay, so there is another multiple steps are in between. The similar step will be there, which I did not denote it just to reduce that time. At the same time, if you really think about, if you feel about SN2 mechanism, so once the protonation is done, then the water directly attack on that particular carbon and it can go out. Okay, so then you produce the intermediate, and then second step will happen. This uh, proton will be leaving, OH will be formed, then protonation will happen over there, then another water will attack, then finally the water molecule will leave and you get the carbonyl compound. Okay, but which process generally takes is the SN1 mechanism, not the SN2 mechanism, because this is at a carbon with having 4 different substituents, so nucleophilic attack will be always hindered. This is another way to identify that which mechanism could operate, is SN1 or SN2. So if you have a sterically hindered carbon where nucleophile cannot approach easily, then SN2 reaction is not that much feasible over there. Then you have to think about the alternative mechanism, which is the SN1 mechanism. Okay, so in this particular case, we have maybe SN1 mechanism following. Again, we can still discuss about the carbon center. So basically, you can see that in this particular mechanism, as I told you, we should always consider the stability of the intermediate carbocation. Now, let's take an example of RCl. So Cl is that living group here, and you are doing the solvolysis. So solvolysis, we are using ethanol water 1:1. So water will attack and produce the corresponding alcohol. Okay. Now the question is that if you see the rate of the reaction, so here you have a butyl chloride, isobutyl chloride. This is tertiary butyl chloride, and then you have allylic chloride, and then you have a methyl allylic chloride. So, or you can say butene, 2-butene chloride, 1 chloride. Okay. So if you see that the rate of the reaction, so in this case this is a bit slow. Then isobutyl becomes a bit faster, then T-butyl become much faster. So if it is SN2 reaction, then the attack from the water from the backside should be hindered, but it is increased. So the mechanism should be something else. What is that? That is SN1 mechanism. Now there is something also we need to understand, that chloride is not a good living group. At the same time, neither water nor ethanol is a good nucleophile. So the reaction for SN1, the compound to follow SN2 mechanism, one important criteria is that your nucleophiles should be moderate or very good. But here both the nucleophiles are very, very weak. So therefore, the possibility of SN2 reaction is very much like negligible. Okay, because the nucleophile is not very at all good. So because if you remember correctly, in case of a SN2 reaction, the nucleophile involves in the transition state. Now, if it is very poorly reactive or it does not react properly, then your reactions will be much more slower. Okay, so that's the same thing. So this is like you can say this is a primary carbon where we do not, it can stabilize the carbocation by 2 hyperconjugation. This is the secondary carbon. You could have 6 hyperconjugations. Now here you have 9 hyperconjugations. So you can see the rate changes from 0.12 to 2100 times. So that is very, very much faster. Okay, now here you have allylic. So now one thing you can try to understand is that here you have a resonance and here you have a hyperconjugation. So you can simply understand that if you have number of hyperconjugation larger, then you could have much faster reaction than simply one of the double bond or unsaturation. Now here it is bit increased because you have another methyl over there, so that can also put involved in hyperconjugation. So 3 hyperconjugation, 1 you have a double bond that increases a bit further. So there is a kind of like impression that you can have that by changing the substrate, how the rate can change or alter. So that is I was talking about. So you have a carbocation, then carbocation can come so over here, and then this is the alpha hydrogen that can involve in the hyperconjugation. So that is the reason why the rate suddenly increased by almost 91 times. Okay, so important aspect is that the addition of salt increases the rate since the added ion replaces the ions from the ion pair, thus inhibiting the reverse step. So there is something that we call salt effect. What is the salt effect in SN1 reaction is that you can add some extra salt which are non-nucleophilic like BF4, PF6. So what happens is that so this reverse step is there. Okay, I already discussed there. Now this is because they are very close. They are different. They're opposite ion pairs. They can easily combine and come back to form the starting methyl back again. But if you think about if you add BF4 excess amount or PF6 ions or anions, then what happens? They replace the bromide from that particular place, and then the reverse step will be reduced, and then you can speed up the rate of the reaction. Okay, that is one thing. So what is the importance of nucleophile here? I already discussed in the previously that it does not involve in the RDS, so it doesn't matter what kind of the nucleophile you have. Okay, in the particular reaction. So basically, the nucleophile is completely innocent in this particular reaction. Okay. Okay. We'll stop here. We can talk in the rest of the part in the next class. Okay. So coming back, sorry for the disturbance. So one good example is the Rita reaction. So basically the Rita reaction where you can see that the SN1 reaction you can use a very bad nucleophile. So if you see that, so you have a like a tertiary butanol. If you add acid, and then you can get the corresponding OH2. So this is then which can release the water molecule and produce the carbocation, tertiary butyl carbocation. And here the nitrile, which is one of the weakest nucleophile, can be used to prepare the t-butylamine from t-butanol. Okay, so you can see that the nitrile can attack on the carbocation, and then it can after hydrolysis you can get the amine. So this is a very good example of that where your nucleophile could be very bad, and that can participate in SN1 reaction. So that with this example, what I'm trying to say is that if you really want to introduce a group which is very bad nucleophile, you should always follow the SN1 mechanism. Okay, there may be some other method you can find in the literature, but if you really want to follow the reaction, it's a very simple way. You can perform the SN1 reaction and you can introduce that compound as a nucleophile. Okay. Okay. So the leaving group is very important here. The reason what I'm saying is that in the rate determining step, the leaving group leaves the molecule. That is the most important, because that is what the R is. Now, if your leaving group is a very bad, or if you have a very strong bond between the carbon and the leaving group, you cannot perform the SN1 reaction. That is very simple. That is very simple to understand. You don't have to think of any other thing, because if the bond is very strong, how this can automatically fall apart. That's very simple. And if you take this example where you have a fluorine, X is just to fluorine, bromine, iodine, and these are the leaving groups basically as a fluoride or chlorides or bromide or iodide, and you can see the bond strength. So the bond strength for carbon and fluorine is the strongest bond, one of the covalent bond, and then that is what the nucleophilicity is very poor. At the same time, the reaction is very slow. Okay, so when you can think that carbon iodine bond is the weakest bond, the reaction is very fast. At the same time, if you think about the nucleophilicity, the iodine is the most the best nucleophile, and fluoride is the worst nucleophile. The reason is that, so if you think is the nucleophilicity is the donation of a pair of electron to the to the carbon center. Okay, now if the nucleophile is strongly electronegative, that will hold its electron very stronger within it, and it not allowed to donate the electrons. Okay, so fluoride is the strongest electronegative element in the periodic table, so it will not donate its electron, and that is the reason why fluoride is the weakest nucleophile. In case of iodine, the 5p orbitals are away from the nucleus and they are more diffuse, and it can easily donate to the carbon center. So that's why the iodide is the best nucleophile. At the same time, iodine is a good leaving group. So the two concepts are different. One case, how easy it can donate the electron. In other case, how weakest the bond is. Okay. So, and you can see in case of iodine, it's a very fast or very good nucleophile. At the same time, the leaving group is very good. And that is the reason why in many cases, iodide is used as a catalyst. Okay. So we will see that if we have find an example in the upcoming slide. You can take another example where you have a oxygen as a nucleophile. So we have a OH minus, we could have a acetate or any carboxylate, we could have water, and we could have a sulfonate. Okay, so here we have to understand the stability of the anion. Okay, more stable, bad nucleophile, more stable, good leaving group. Because if it is a stable carbanion that can easily leave the molecule, and then it would be satisfied with the electronic configuration whatever left. Okay, so you can see here, so OH minus or hydroxyl ion is very fast nucleophile. Nucleophilicity is very strong. On the other hand, the sulfonate, which is very slow. Okay, if you see about the nucleophilicity, so the pK is very high of the OH minus, okay, or a hydroxyl group, and this is a very bad leaving group. Okay, or poor, and this is a very good leaving group because it is stable after it leaves the molecule. Okay. Okay, so it's a catalyst what I was talking about. In many of the SN2 reaction, we use iodide as a catalyst. So for example, here you have a chlorine or bromine, so benzyl fluoride or benzyl bromide, you want to substitute with the cyanide. Okay, so you can use sodium cyanide as a nucleophile, and then DMF. So now here DMF is used to stabilize, to dissolve the sodium cyanide. Okay, now because the chloride or the bromide is a bad leaving group, then what we do basically, we use catalytic amount of sodium iodide. So sodium iodide is at first replace the, because it's a very good nucleophile, so you can replace first that chloride or bromide, and then it becomes a very good leaving group. You can use, then the cyanide can attack, and then again the iodide can come out of the molecule. So this is very common practice in organic synthesis that they use this like sodium iodide as a catalytic amount to speed up the rate of the reaction. Okay. Okay. Now one may ask, sir, what about the rate of the reaction? Is it sorry, mechanism, SN1 or SN2? Now in this case, there is a very difficult to say, because you have a like not that much sterically hindered, so SN2 is possible. At the same time, you have that double bond is there, so that can also stabilize your carbocation. So you may have a few amount of, or few portion of the molecule going to SN1, few portion of the molecule can go via SN2 reaction. Okay, so they are very like a moderate sterically hindered, so we cannot really say exactly what except for the reaction is mechanism it is following. Okay. Okay, so so there is some other things that what about the react site? Okay, so in the case of SN2 reaction, we always seen that nucleophile will be coming always from the react site. Okay, now OH minus is a bad leaving group. This is a very important thing you also should learn, is that if you have a very bad leaving group, you can convert this bad leaving group into a good leaving group. And the example is that if you take this alcohol and then you treat with the HBr, okay, then you can produce OH2 plus, which is a very good leaving group, and then your bromide can attack from the back side and you can easily get the substituted product. But there's something important to understand, is that if your OH2 plus leaves, or water molecule leaves the molecule before the bromide attack, you produce a carbocation. Okay, then many things could happen. So always, then you can have a racemization, you could lose the enantiomeric pure compound that you started with. So there is a something you have to always understand, that what I really am doing. So because OH2 plus water molecule is a very good leaving group, so they can easily leave if the R can stabilize the carbocation. Okay, so then you lose the enantio selectivity. Okay, that because you can may proceed towards the complete racemization. So this is another way you can solve this issue. So you can react with the tosyl chloride. Okay, so the OH will be react with the tosyl to get the OTS. So para-toluene sulfonyl chloride, and then you can use pyridine as a solvent, but that is actually a nucleophilic catalyst. I will discuss just a few minutes later. And then what will happen, then that OTS can be replaced by bromide, because OTS is also a very good leaving group, or tosylate OTS minus. Okay, so in this, in the left side case, you can actually stop racemization, but in this case you may have racemization depending on the R. If R cannot stabilize the carbocation, then no need to worry. Okay, if R can stabilize the carbocation, then you have really need to think about you should take this pathway or you should take this pathway. Okay, now this mechanism what I have discussed here, that what happened when you have, this is the tosyl chloride TSCl. So first pyridine attack on the sulfur, it kicked out the chloride, and then you produce this particular intermediate, and then pyridinium is a very good leaving group, then alcohol attack on this particular sulfur, and that pyridine goes out of the molecule, so you get the tosyl molecule. So this is, we call this nucleophilic catalyst, okay, because it's a nucleophile. Okay, so in this reaction, pyridine is used as a solvent, but always remember pyridine is not a good solvent. It has very much bad effect to our cells. So whenever you are dealing with the pyridine, you should be very careful of using it. Don't smell it; it's a very bad smell. I used during my MSc research, so that's you should take care very carefully, because that can damage your biological system. Okay, so that's what I was talking about. If your R is stabilize the carbocation, then it may proceed via SN2 reaction, SN1 reaction. If it doesn't stabilize, then it can proceed via SN2 reaction. So this is the something that we always should remember. Now, what about the electronic effect for this? The benzyl group favors both the mechanism that we have discussed already. Okay. Now, if you have OME, like a methoxy group at the para position of the benzene ring, then you can favor towards the SN1 mechanism. Okay, but we cannot say that the reaction should like only take the SN1 mechanism, because this molecule is still not that much sterically hindered, and then cyanide is a good nucleophile, so you have a chance of both mechanism operating parallelly. Okay, then when you have a nitro, then you cannot stabilize the carbocation, then only SN2 is the possible pathway to follow. Okay, so this is what I have said, that because nitro is electron withdrawing group, so you produce a partial positive charge here, this is another partial positive charge, so they will repel each other, so your carbocation will never form, so then your SN2 mechanism is the favorable pathway. So there is something I have given you the rate. You can see for the OME the rate is 2500, and then you can see that hydrogen gives you 1, which is like the reference, and then for the nitro it goes down like 10,000 times it goes down. So this is like very much clear to us that in this case, now here you can see you have used methanol. So methanol is not a good nucleophile. So the only one pathway is the SN1 mechanism. So nitro group, which is electron withdrawing group, that destabilize the carbocation, what I was talking about here. So then you have only possible pathways SN2 mechanism. Okay, but because the methanol is not a good nucleophile, so SN2 mechanism also does not operate here. So only pathway is SN1, and that actually very much slower process. Okay. Okay, so there another example I would like to mention here is that that is called alpha halo keto compound. So alpha halo keto compounds are very important compound, and they are very much good at SN2 reaction mechanism, but they are poorly reacting SN1 mechanism, because if you produce a carbocation, this carbon is also electropositive because of oxygen is electron withdrawing group. So positive and positive, so SN1 carbocation is unstable, so SN1 is not possible. But why SN2 is favorable? Because where, if you remember that when nucleophile attacks with the antibonding of the CBr bond, which is around this region. and pi star orbital of this bond, this carbonyl bond is also can happen or can be over there. Sorry, not pi star, pi orbital. So this pi orbital and sorry, pi star and sigma star, sorry, not pi orbital, pi star and sigma star, they will form a larger orbital where the nucleophile can easily attack. So that is the reason why this is I have taken from the Claydon book, and you can go through to understand better. Okay, the solvent effect is the most important here. We always remember that in SN1 mechanism we produce the ionic species, and that means that the solvent you are using here should be always polar protic solvent to stabilize both the carbocation as well as the anion. So anion could be stabilized by hydrogen bonding, so that will takes the bromide or the any anion away from the molecule, and also the dipole-dipole interaction can stabilize your carbocation. Okay, and so polar protic solvents are always good for the SN1 reaction. What about the SN2 reaction? If you use polar protic solvent, your nucleophile will be solvated. That is the problem here. So your nucleophile will be solvated, and you can think of if you have a very like a nucleophile which is here at inside, and then you have a solvent shell around the nucleophile. Then when the nucleophile will attack the carbon center, it has to remove all the solvent cell and come out of the from the solvent cell to react. So if you have a polar protic solvent, it will be strongly hydrogen bonded, and then it cannot come out. So that's the problem. So you should not use polar protic solvent when you are performing the SN2 mechanism. But you have to use polar solvent to dissolve all these nucleophile, because they are ionic compound. To dissolve the ionic compound, you need polar solvent. Okay, like sodium cyanide or sodium bromide if you want to substitute the bromide. So all these cases you have to use polar aprotic solvent for SN2 and polar protic solvent for SN1 reaction. Phase transfer catalyst, we can talk about this in the next class. Okay, thank you very much.